Okay, so this will be part 2 to the videos on neural communication. So make sure that if you haven't watched the part 1 video, that you do watch that. That does an introduction to the nervous system and neural tissue and neural communication, and also covers the resting membrane potential. This video is going to do, at least on the little outline from part 1, that was covered in part 1, this will be step 2, which deals with graded potentials. And so you'll remember from the first video that I'll talk about that the main goal here in neural communication is the generation of action potentials. And I kind of equated this to initiating nuclear holocaust, pushing the proverbial button. And so we started in the last video, we covered resting membrane potential. So what is the foundation that where is that foundation where the cells are, the neurons are for neural communication? Now in step 2, graded potentials, you can see that graded potentials in the analogy is moving your finger either closer to or further from the button. And remember, if you push the button, we initiate nuclear holocaust. That is an action potential. So just make sure when we talk about graded potentials, it's moving your finger either closer to or further from the button without touching the button. So if you think about initiating nuclear holocaust, launching nuclear weapons as exciting, so moving your finger closer to the button is excitation. Moving your finger further from the button will be considered inhibition. So let's kind of just do a brief little review from video 1. This was an important slide there, sort of a summary of everything we looked at, is that when you look at a resting membrane potential, or what causes the resting membrane potential, remember at rest, we have inside the cell. Let me just touch up a few things here. So this is inside the cell. This is outside the cell, or in this case, outside the neuron. And we can see inside the cell, potassium is more highly concentrated. Outside the cell, sodium is more highly concentrated. And at rest, that difference is a value of negative 70 millivolts. So the inside is 70 millivolts more negative than the outside. So we went through in the last video, we talked about the electrochemical gradient, and we know that at rest, the potassium ion kind of sort of wants to leave the neuron, and the sodium ion really wants to get in, but they can't. Why was that? So just take a moment here, pause the video, and think about why is it that the ions, even though they want to move, they can't move? Okay, so hopefully you had a chance to answer that they can't move because of the gates. There are potassium gated channels and there are sodium gated channels that at rest, they are closed. So the ions cannot move across that semi-permeable membrane. But then how do we get each ion to move? So pause the video, think about that. Of course, when we're trying to get the ion to move, if it's the closed gates that prevent the movement, if we want to allow the movement, then we need to open those gates. And we talked about a couple different gates. We talked about the chemical gates that open and close in response to chemicals, specifically neurotransmitters in this case. We talked about voltage gates, which open and close in response to specific voltages. And we'll see that later on. Obviously, an example here of voltage is negative 70 millivolts. And then there were mechanical gates that open and close in response to physical distortion of the membrane. So in all of these cases, this talks about stimuli that open and close the gate. So if we want to get the ions to move, we must open the gate. And depending on which gate it is, which type of gate, tells us what specific substance is required. So when we talk about graded potentials, you just need to put in your head that for the most part, especially for simplifying for this chapter, you just need to put in your head that we are talking about chemical gates. There are cases of mechanically gated receptors causing graded potentials, but for this chapter, to simplify, I want you to associate graded potentials with chemical gates, and I want you to associate action potentials with voltage gates. So let's look at what a graded potential is. This is how I define it. A graded potential is any change in the resting membrane potential from rest. I guess that's a little duplicate there. Let's say we can just eliminate this. So we can say a gradient potential is any change in the resting membrane potential. I guess one important little caveat to add is that it is sub-threshold. Now this is a term that I haven't mentioned a lot, is threshold, but just already know that threshold is kind of the end goal. Threshold represents the value of the action potential. So when a neuron's membrane potential reaches threshold, you have pushed the button and you have generated an action potential. Well, remember, a graded potential is the movement of your finger up or down or closer or further away from the button without pushing it. So pushing the button represents threshold. So what is a graded potential? Any change in the resting membrane potential. So that means it could be a change in the more positive direction. So if we're starting at -70, moving towards 0, or any change in the more negative direction, more negative than -70 or further from 0. So tying in from our last slide, if a graded potential is any change in the resting membrane potential, what must happen to change the resting membrane potential? So pause the video, take a moment to think about that. To answer this, we have to think about what was it that caused the resting membrane potential to begin with? It was the separation of the ions. It was the fact that those gated channels are closed so the ions remain separated. So if I'm telling you that a graded potential is any change in the resting membrane potential, then to change the resting membrane potential, we need to move the ions or one of the ions. To move the ion, we have to open the gate. To open the gate, we're talking about chemical gates, you must have a neurotransmitter. So do you see the connection between each of these steps? So it's sort of like riding a bike. You got to do step 1 and then step 2 and then step 3. You can't do them out of order. So when we look at a graded potential, as I already mentioned, can be in a positive direction or in a negative direction. If it's in a positive direction, meaning moving towards 0, then we call that a depolarization. If it's in the negative direction, as in away from 0, or specifically away from threshold, away from action potentials, then that's called a hyperpolarization. So to put this another way, a depolarizing graded potential makes an action potential or makes reaching threshold more likely, and a hyperpolarization moves you further from threshold and makes an action potential less likely. Graded potentials are also described as being decremental and varied. Decremental meaning that they decrease in their strength. And varied means that obviously they can have different strengths. And so the best analogy I think about is dropping a pebble or a rock into a perfectly still and flat pond. Obviously, the bigger the rock, then the bigger the change or the bigger the ripples in the water. So graded potentials are the same way. If you think about a graded potential, a small graded potential is like a small rock in the water. So you will have a change, but the ripples will be very small. They will not last very long. If you throw a big rock in the pond, then you're going to have much bigger ripples. They will last longer. But either way, the further away the ripples go from the source, from where the rock first hit the water, the ripples get smaller and smaller. So that's what we mean by decremental and varied. And just to, as I've already kind of used this language here, the goal of a graded potential is either to make action potentials more likely or less likely. So if a graded potential is going to make an action potential more likely, we're going to call that excitation, or depolarizing graded potential. If we're making the action potential less likely, then it's inhibition, inhibitory, or a hyperpolarization. So we have seen this image before, looking at the inside of our cell. The inside versus the outside of our cell, of our neuron. So I want you to think about this. If you are starting at rest, meaning we're starting at -70 millivolts, this is a question. I want you to try to apply this here. I'm telling you that you are in charge of this cell And I want you to make the membrane potential, instead of -70, I want you to make it -75 millivolts. Let's assume that each one of these positive ions represents a 1 millivolt change. So I'm asking you to move 5 of these ions. So I want you to think about it. If I want you to go from -70 to -75, which 5 ions are you going to move? Are you going to move 5 potassium ions from the inside outside, or are you going to move 5 sodium ions from the outside to the inside? So definitely pause the video and give yourself a chance to think about this, because if you can answer this correctly, then that's going to really show you that you know this concept. You are understanding what is happening here. So pause the video. I will go over the answer. But remember, the question here is, which ions are you going to move to make the membrane potential -75 millivolts? Okay, so hopefully you've had a chance to think about this. When we're answering this, we need to look, what are we trying to do? Are we trying to make the membrane potential more positive, meaning move it towards zero, threshold and towards zero, or are we trying to make it more negative, moving it, or are we trying to move it away from threshold or away from zero? Well, in this case, -75 is more negative than -70. So we need to think about which ion, the movement of which ion is going to make the membrane potential more negative. So let's look here. Let's start with potassium. Potassium is positive. So potassium ion is positive. If we move 1 positive out, what does that mean? Well, we know from the membrane potential and from video 1 that the inside of the cell is already more negative. Well, just mathematically, what does it mean that if you remove a positive ion from an area that is already negative? That means you're going to make that inside even more negative. Well, look, that's exactly what we want to do. We want to make the membrane potential more negative. So to answer this question, we want to move 5 positive potassiums out of the cell. If we reverse this, if we moved sodium in, that means we're adding positive into a negative area, which would make the membrane potential move in a more positive direction. So just know, if we want to make, this shows us, like I said, if you got this right, you understand that, then it means you're really starting to understand this concept. But just in case, obviously it's much better that you understand how we got here, but just to give you a summary of everything that I've talked about now, and even from video 1, that's what I want to use here for this slide. So just to kind of get where we started, is that we were at -70. I don't know why my pen's not working very well. Hope that works. So here we are, -70 at rest. Let's move this way, and let's call this negative. We'll call this -85 millivolts, and let's move in this direction, and we will call this -55 millivolts. And just so you know, -55, this value here, is the specific value of threshold that I have mentioned. So at this point of -55 is when we generate an action potential. So action potential at -55, -85 millivolts doesn't have a special name, but I'm just using -85 because if we're going 15 millivolts this way to threshold, then I'm just going to use -15 in the other direction as another reference. So you can see -7, of course, zero millivolts is up, would be even further away. So we see -70 to -55, and then we see -70 to -85. So when we move, let's start in the negative direction. So -70 to -85, we know this is a graded potential because it's any change in the membrane potential from rest, but this is in a negative direction. So we call this a hyperpolarizing graded potential, because we're making the membrane potential, we're making the separation even greater, -70 to -85. So a hyperpolarizing graded potential, we have to think what causes the hyperpolarizing graded potential. Well, what causes that is the movement, or let's see, which order do I want to do this? What causes the hyperpolarizing graded potential is we have to lose potassium ion. So potassium ion moves out of the cell. Potassium ion moves out of the cell. For that to happen, it means we must open the chemically gated potassium channels. And remember, what opens chemically gated channels? Neurotransmitters. Well, neurotransmitters come in two varieties, either excitatory or inhibitory, depending on what the result is. Well, if we're going from -70 to -85, is that excitatory, moving towards threshold, or is it inhibitory, moving away from threshold? Or moving away, so it's inhibitory. So this is as a result of inhibitory neurotransmitters. Well, let me just do the other side here. So if we're moving towards threshold, this would be a depolarizing graded potential. Depolarizing graded potential, which is a result of sodium ion moving into the cell, which we know then is only allowed by the opening of the chemically gated sodium channels. So chemically gated sodium channels. And since this is moving towards threshold, it is as a result what opens chemically gated channels. These would be neurotransmitters. So this would be as a result of the arrival of excitatory neurotransmitters. So even if you don't understand how we got here, I want you to memorize this information, because there will be a lot of questions based around this information, and you can see how everything is connected. So it's the same concept, but there's about 4 different terms describing the same type of change in the membrane potential. So just to help you practice, I'm not going to go over these answers, but here are some review questions to think about, to ask yourselves, or even to email me about in response to an excitatory neurotransmitter, which gates will open, the opening of which gates will cause a depolarizing graded potential, and then chemical or ligand gates open in response to specific what, and voltage gates open in response to specific what. So think about those. This will give you a chance to test yourself, test your understanding, and as I said, certainly reach out if you have any questions.